Great. I'm really pleased to be here. I haven't actually seen Willem present that before, just to see comprehensively everything that Adair has achieved just in the 2 short years that we've been put together. It's really great to see so many students progressing on their coursework, the interactions that we're developing with partners. I felt really proud to be part of such a really strong group. So I was given a fairly open-ended scope for what I should talk about today. Anything related to the environment and data science and some of the work that we're doing. So what I thought I would do is just give you a bit of a flavor of some of the systems that we work in, some of the challenges that we see in applying data science methods in the natural environment when we're trying to manage things like vegetation or manage water resources, and some of the work that we're doing at the University of New South Wales with our students and potentially some of the students who are coming through DARE as well, about how we model the environment and some of the data science opportunities in modeling the environment. So just to give you a bit of an idea about the difficulty and the complexity of the systems that we work in. The figures here are taken from a paper that a former postdoc of myself and Fiona Johnson, who is another investigator in DARE. That's okay, yep. Sorry, the screen's going up here. Another investigator in DARE recently published, that was really looking about the interactions between soil processes, hydrologic processes, climatic processes and vegetation, and how that varies across the landscape and how it might respond to changes in the landscape. So any shifts or non-stationarities that occur in the landscape. And hopefully what you can see from that is that we are looking at very complex, non-linear, dynamic sorts of systems that have all of these feedbacks and interactions that occur over a range of different scales. And so the figure on the right there shows how that might vary at the patch scale up to the landscape scale to sort of more broadly as well. And so the challenge for us then is to take all of this complexity, all of this nonlinearity, all of this variation over a range of different scales and turn it into a really tractable modeling framework that is fit for purpose, that we can use for things like understanding how our water resources are going to change under a future climate, to understand how fire or changes in vegetation might impact our soil properties or our water resources. But fortunately for us, over the last few decades, there has been an explosion in the sorts of process-based models that are used by hydrologists and other sorts of environmental modelers. So the figure that I have on the bottom right there is just an example of a very simple type of hydrologic model that incorporates some of these feedbacks, but only has a few parameters associated with it. In spite of that, it is a representation of the processes that we think are occurring in the landscape. And so we refer to this as a conceptual or occasionally a process-based type model. And as we start being interested in using these models for different types of applications, we can expand them to incorporate different types of variables as well. And so this is another paper that was published by a former postdoc and student of mine who was looking at water quality variables and thinking about how hydrology might be driving variations in water quality and some of the uncertainties associated with that. And we can extend it again to be looking at not only water quality and hydrology, but then also say vegetation. So this is another paper that was developed by another student of ours and that we're continuing to work on at the moment, that is looking at feedbacks between water and vegetation, how they might change under a changing climate. So all of these existing models that are representations of the processes that are occurring in our landscape or in our environment, and that are fairly simple and tractable and can be used for water resources management, can be used for running scenarios, can be used for a whole bunch of operational purposes that people in the community might be interested in. Now, alongside this growth of these sorts of tractable modeling frameworks, we also have an increase in the types of technologies that we have to observe the landscape and to observe the environment. So a real increase in using things like remote sensing at very large scales to be able to look at water resources or to be able to look at vegetation. So we can do that at large scales and then over fairly significant timeframes as well. These systems have been in place for a large number of years. And on top of these sorts of large scale remote sensing technologies, there's also been a growth in the sorts of things that we measure actually at the landscape scale or at the catchment that we might be observing. So this is a catchment that I was working with over in America. I think it is one of the most instrumented catchments in the world, where we were able to observe at a point things like groundwater, like how snow melt. We were looking at eddy covariance, so we could actually measure water fluxes in the air as well. And so we can use then this type of data to be able to infer what might be occurring at a smaller scale, and then relate that to, say, remote sensing data that is a much larger scale. So we've had this significant increase in models and this significant increase in data and observations at the same time. So as someone who is interested in data science, then the challenge is, well, how do we relate these two? How do we relate the sorts of models that we have with all of this data and observations that we have in a way that appropriately represents or recognizes the uncertainty associated both with our models and also with our observations, while producing a framework that is usable, that we can use in operation. So just a small challenge for all of us who might be interested in data science. But at the same time, we're seeing a growth in different sorts of data science methods as well. So we can see an increase in uncertainty frameworks that try to explicitly recognize some of these different sorts of uncertainties. So uncertainty in observations and uncertainty in models. And each of these different uncertainty frameworks is really aimed at trying to relate those two things, trying to relate the model with our observations that we have, our data. So that's really where a lot of my research is pitched, in trying to relate the observations that we have with some representation of the processes that are occurring in the environment. And the nice thing about that is that Bayesian inference is a really attractive and elegant approach in which we can easily relate those two types of information that we have, information from data, information from a model, and explicitly take into account all of the different types of uncertainties that we have. The standard Bayesian model is fairly well established in my field, where you develop a model that conditions your observations on the process-based model that you have. And now it is easily extended to take into account some of the emerging technologies and emerging approaches that I was talking about previously. So things like multiple sources of data, being able to expand your model so that it varies through time, so it's hierarchical and can be changing under non-stationary conditions, or being able to incorporate multiple models into a single framework. So multiple hypotheses about how the system is working. So then if we think that we have all of these tools available to us, we have models, we have new data, we have new ways of being able to reconcile those models and that data, then what do I see as some of the opportunities and challenges? I'm going to frame them all as opportunities though, in using data science for trying to quantify uncertainty in the environment. And I just thought I'd give you a very brief taster of some of the things that I've been working with. So one of the things that our research group is really interested in, and we'll have a student who'll be working on this, is thinking about the complexity of errors in the models that we are using. So in the example that I've given here, and I know there's a lot of information there, but there's a reference if you want to look elsewhere. We are dealing with both hydrologic models and also water quality models, but these models show a high degree of heteroscedasticity, so very complex variance associated with the errors in the models. They tend to be zero inflated because environmental data often has long time series where nothing happens. We might have an ephemeral stream, or we might have a situation where there is no water quality problem and suddenly there's a very high water quality problem. So zero inflation, heteroscedasticity, and also things like autocorrelation mean that we have these really complex errors, but we want to be able to try to characterize those errors. We want to be able to take into account this time varying nature of the uncertainty. And so we're developing new types of frameworks for being able to properly model some of that non-stationarity or that variability that we have in the uncertainty associated with our models. Another thing we're looking at that's really strongly related to that is then, well, can we think more carefully about the uncertainty associated with our measurements so that we might be able to use different types of data to be able to calibrate our models or to condition our models. And a really common example, and I've got a student who's working on this at the moment, is when we're trying to calibrate a water quality model and we can't observe the variable that we're most interested in, because logistically it's really quite hard to go out and take measurements of different types of nutrients or things that might be very dynamic or might require lab access to be able to process the measurements. And so in this case, we're interested in using proxy data. So can we use things like temperature or turbidity or other sorts of measurements that are really easy to get at as a way of calibrating our model? And so then we're interested in taking into account, well, the uncertainty associated with the proxy. So we're calibrating our model not with the variable that we have, that we want, but the variable that we have. So more complexity associated with our measurements. Another project that we're looking at, and I can't give a DARE presentation without putting a few equations in there, but there is a reference there if you're interested in looking at that a little bit more. But another project that we have is thinking about, well, this emergence of remote sensing technology and the fact that it's very difficult to be able to characterize the uncertainty associated with the retrievals that we get from the satellites when we're using this remote sensing data. And the nice thing about a lot of satellite retrievals is that they'll give you additional information or metadata about your observations and tell you whether it is a good measurement or a poor measurement. So we're developing different types of error models that allow us to take into account that metadata or that extra information that we get from a satellite, but still be able to use the data. So we don't throw out data that might be a poor measurement. We just recognize that it has more potential uncertainty associated with it or more error associated with it. And we use that to be able to calibrate our models as well. And then finally, one thing that we're starting to get more interested in, we've had a number of papers just over the last 2 years around this. We have a couple of students in DARE who will be working on this as well, is thinking about, well, how can we harness the power of machine learning or different techniques in AI, while still being able to use our knowledge about the processes that are occurring in a catchment or on a landscape or in the environment. So can we use process-based models, but then also machine learning models or machine learning methods as a way of combining the sort of potential predictive power that you get from a machine learning approach, but the ability to extrapolate our model to unknown conditions that we think we would get from a more process-based model that is a better representation of the processes. And so what we're doing in this case is trying to develop hybrid models. So models that combine together a process-based model, so we might have a distributed, physically based, hydrologic or ecosystem type model with a machine learning model. And in this case, we're using an LSTM, it's a type of neural network, to represent any unknown conditions or uncertainty that we have in that process-based model. And so we couple the two models together and we end up with a better representation of uncertainty and a better prediction, but we still have those underlying processes represented within the model. And so this is something that is just emerging in my domain. It's something that we think is pretty exciting, the idea of using hybrid or coupled models. And so we'll have a couple of students who will be looking at this. But where I just wanted to leave things was really the challenge and the opportunity that I think we see in our research is in being able to use data science to better relate our data with our processes or our representation of the system. And I think that's really at the heart of DARE as well. The students who are coming through DARE are co-supervised by someone who has domain knowledge, who might be a representation of that process model, and then an expert in data science who would be a representation of the way in which we model those errors, the way in which we model our data. And so that's really where I'm positioning a lot of my research, where our research group is moving, and where I think the challenge will be for us in developing new types of data science methods. So just to finish up, hopefully you saw at the beginning of that, we are now seeing this increasing desire for really multivariate and multidisciplinary models. When in the past we would have models that just focus, say, on water for doing water resources management. Now we're increasingly interested in being able to incorporate lots of other processes into our model. And fortunately, there are lots of existing models out there that do that and that are used for different sorts of operational environmental applications. But some of the recent things that we have been working on, I think, have really demonstrated the need that we need better ways of representing multivariate data errors. So being able to use data science to represent the complexity of our uncertainty. And also we need to start thinking about, well, how do we capitalize on the benefits of both of our fields? So how do we harness the benefits of both process type models and then also potentially machine learning or data science methods so that we have improved predictions overall? I think I finished right in time and hand over to Richard, I'll hand over to Willen, who can do the pass on.
Yeah, I think we have maybe room for one quick question if anyone has a question.
Thanks, Lucy. That was really interesting. I'm going to ask a mathematical.
Oh, okay. That's a bit of a challenge here.
So you have, Y conditional on X, I think.
Yep.
Y was remote sensed data and X was a model.
Yeah, so X is an input. Yep, and we have parameters as well.
What you're trying to do there, I think, is to improve the quality of your sensed data using model inputs. It could, of course, be the other way around, where you try to improve the quality of model predictions using sensor X conditional on Y. I mean, where do you see it going? Both as powerful as each other, or in your field, or?
I think they're both completely interrelated, and I don't know that we can separate the two. So what we're trying to do is ultimately improve our use of remote sensing data, but for a model. And so we want to improve the model. That's the ultimate goal, is we want to be able to use that model for predictions. But it's in understanding the value of the remote sensing data at different times to be able to ultimately improve that model. That makes sense.